Welcome to the deep dive. Today, we have a really fascinating stack of sources in front of us.
Yeah, it's a really incredible collection of research today.
It is. We are pulling from cognitive science research, neurobiological studies on math learning, and even some instructional design frameworks. And our mission for this deep dive is straightforward, but, highly ambitious.
Definitely ambitious.
Right. We're going to decode why learning math so often feels like hitting a brick wall. We're going to prove to you that your brain is absolutely not broken, and we're going to reveal how true, lasting learning actually works, like on a biological level.
I love that we're tackling this because it's so universal.
It really is. And to get us started, I want you to picture this. You were sitting at a desk. Maybe this is a really visceral memory from middle school, or, maybe it's you right now, sitting at your kitchen island trying to figure out a complex budget.
Oh yeah, we've all been there.
Exactly. You are staring at a multi-step math problem. Your pencil is just hovering over the paper. You are completely frozen. The clock is ticking, the fluorescent lights are humming, and you are experiencing what researchers literally call the space out.
The space out, yes.
You can just stare at that blank page for 20 minutes without making a single mark. Or, maybe you're the other type of student. Maybe you fall into perfectionist paralysis.
Where you're just constantly second-guessing yourself.
Right, where you write down a number, doubt it, erase it, write it again, erase it again, until the paper literally tears.
It is an incredibly isolating, panicked feeling. And you look around the room, and it seems like everybody else's pencil is moving.
Yeah.
And the immediate, visceral conclusion that most of us jump to in that moment of paralysis is just, well, I am just not a math person.
Yeah, you just think, my brain simply does not work this way.
Exactly.
That hovering pencil just feels like a massive personal failure.
Yeah.
But, and this is the core of today's deep dive, the research we have tells a completely different story.
A completely validating story. The overarching theme across all of these neurobiological and cognitive studies is just so reassuring that freeze response, it doesn't mean you lack intelligence. It doesn't mean you don't have a natural aptitude for numbers.
Wait, really? It's not a capacity issue?
Not at all. It means your brain is doing exactly what it has been biologically hardwired to do when it faces a systemic overload. The root of the problem isn't your cognitive capacity. The issue is that math is frequently taught in a way that aggressively overloads human cognitive architecture.
Okay, so if the brain is biologically hardwired to freeze under these specific conditions, we need to understand the physical bottleneck here. Like, why does the system crash in the first place? Because you always hear people say things like, oh, I just can't hold all these numbers in my head.
And that phrase is incredibly scientifically accurate. We are talking about working memory here.
Working memory.
Yeah, think of working memory as your brain's temporary mental scratch pad. It's the active, conscious workspace where you hold on to rules, numbers, and procedures while you are, actively trying to solve a problem.
Right, okay.
And for a long time, the golden rule of psychology was that human beings could hold about 7 pieces of information in this space at once. That's actually the historical reason why standard phone numbers are 7 digits long.
Oh, wow. I never put that together. But the newer cognitive science models in our sources, they suggest that for something as demanding as mathematics, that scratch pad is actually way smaller.
It's significantly smaller, yeah. We now know that for complex interactive tasks, your working memory can actually only hold about 3 to 4 chunks of information.
Only 3 to 4.
Just 3 to 4. And it can only hold them for roughly 30 seconds before the data either degrades, is lost entirely, or, requires you to actively expend a ton of mental energy just to refresh it.
3 to 4 chunks. For 30 seconds. We are operating on an astonishingly small margin of error here.
Exactly. And mathematics is characterized by what researchers call incredibly high element interactivity.
Element interactivity, meaning just a lot of moving parts.
Right. There are a massive number of moving part symbols, rules, magnitudes, and they all interact with one another. You have to hold all of them in your conscious mind at the exact same time to make sense of the overall problem.
Okay, I'm thinking of the classic algebraic bottleneck that literally every student hits at some point.
Oh, the multi-step equation.
Yes. You're staring at a multi-step algebra equation. The overarching goal is to isolate the variable. But right in the middle of step 2, you suddenly have to, multiply 7 by 8. Or you have to convert 0.5 into a fraction.
Right, a basic arithmetic hurdle.
Exactly.
Yeah.
And you end up expending an enormous amount of conscious mental effort just trying to retrieve what 7 times 8 actually is. And by the time you figure out it's 56, your brain completely locks up.
You completely lose your place.
Yes. You've forgotten where you were in the algebra problem. The algebra itself wasn't the hurdle. It was the 7 times 8 that hijacked the entire system.
And in cognitive science, that lockup is a prime example of cognitive overload. I mean, your working memory only had 3 or 4 available slots to begin with. You used one slot to hold the foundational algebra rule, another slot to track your current physical location in the equation, and then you had to dedicate your remaining slots to manually calculate 7 times 8.
So you literally just run out of mental workspace.
You run completely empty. The overarching equation drops out of your short-term memory because there is physically nowhere left to store it.
Okay, let's unpack this. So it's essentially like trying to run a heavy, complex video editing program on a decade-old computer with barely any RAM.
That is a perfect analogy.
Like the computer itself isn't broken. There just isn't enough active memory to process those high-definition video files. And to take that further, sitting in a math classroom usually means you also have like 40 background internet tabs open at the exact same time, playing music and showing ads.
Yes. And those background tabs are such a crucial piece of the puzzle because in an academic setting, one of the most resource-heavy background tabs draining your mental RAM is anxiety.
Oh, of course, math anxiety.
Right. When you feel anxious about math, your brain automatically dedicates a portion of your already limited working memory to monitoring that psychological threat. You are using active brain power to worry about looking foolish or, stressing about an upcoming grade.
Which leaves even fewer slots available for the actual mathematics. That is wild. But hold on, I have to push back here.
Okay, go for it.
If our working memory is this fragile and our mental RAM is this limited, why is the standard model of education built around a teacher writing a massive 15-step problem on the whiteboard while the students just copy it down?
That is the million-dollar question.
Right. I mean, for hundreds of years, the teacher writes, the student copies. It worked for generations. Are these instructional designers really saying standard practice is biologically wrong?
They are arguing that it often creates entirely unnecessary barriers to learning. Cognitive load theory breaks the demands on your brain into different categories. There's intrinsic load, which is the natural, unavoidable difficulty of the math itself.
Okay.
But then there's extraneous load, and that is the unnecessary mental effort caused by poor presentation or inefficient teaching methods. A classic offender here is what they call the split attention effect.
Oh, I remember this vividly from geometry. The teacher would project a highly complex geometric diagram on one side of the whiteboard and then write a massive paragraph of text explaining the properties of that shape on the completely opposite side of the board.
Exactly. And your eyes are forced to dart back and forth between the text and the diagram.
Yeah, you read a sentence, try to hold those words in your tiny working memory, look over the diagram, try to map the verbal description to the visual angles,
And then hold that new connection in your mind while you look back for the next sentence. It is cognitively exhausting.
and it has absolutely nothing to do with learning the actual principles of geometry.
Nothing at all. It is purely a byproduct of bad design. And when students are repeatedly subjected to this kind of extraneous cognitive overload, they resort to a biological survival mechanism. They start mimicking.
They stop trying to process the logic and just blindly write down whatever the teacher writes down.
Exactly. They fall into what the research labels the algorithm trap. Because their working memory is entirely overwhelmed, students stop seeing mathematics as a logical system of values and quantities. They just start seeing it as a meaningless vertical list of isolated digits to copy.
I'm trying to picture what that mimicking looks like in real time. It sounds like when kids memorize the steps for long multiplication, say 99 times 27.
Yes, the standard algorithm.
Right. They know they have to multiply 7 by 9, write down a 3, and quote-unquote carry the 6. Then they multiply 7 by the other 9. But they treat that second 9 as just a single digit.
They don't process it as 90?
Exactly. They've completely lost sight of the actual magnitude of the numbers because they are just executing a robotic script.
And the problem is, they have acquired procedural knowledge, but it's incredibly fragile. They know the how, but they have absolutely zero understanding of the why.
So if things change even a little bit.
Right. If the parameters of the problem change even slightly, they freeze. For instance, if the teacher presents those exact same numbers within a word problem instead of a neatly stacked equation, a student who only mimicked the steps will completely lock up.
Because their memorized script no longer applies.
Exactly. Because they don't understand the underlying logic of base 10 multiplication, they have no mental tools to adapt to the new format.
Well, if copying creates fragile knowledge, and our working memory is too small to handle complex problems all at once. How did anyone ever build the pyramids? I mean, how does true mathematical learning actually happen if the human system is this limited?
Here's where it gets really fascinating. The answer lies in a cognitive process called chunking. Yeah, chunking is essentially the holy grail of mathematical proficiency. The fundamental difference between a novice math student and a math expert is not raw brain power. And it certainly isn't a larger working memory capacity.
Right, we already established that's biologically fixed.
Exactly. It is entirely about the ability to group information together.
Okay, let's visualize that. Take the algebraic expression, open parenthesis, a plus b, close parenthesis, squared.
Classic binomial.
A novice looks at that and sees a chaotic jumble of separate overwhelming elements. They have to process the parentheses, the individual letters, the plus sign, the exponent. It maxes out their working memory instantly because each symbol demands its own slot.
Right. But an expert looks at that exact same expression and sees something entirely different. They have seen that specific pattern so many times, and they understand the mathematical relationship behind it so deeply that their brain automatically binds all those separate symbols together into one single familiar object.
So to go back to the computer analogy, chunking is like taking 40 separate heavy image files that are actively crashing your computer's RAM and zipping them into one neat, highly compressed folder.
A zip file. That is brilliant. Yes. Now it's just one single file. It takes up a fraction of the space and is incredibly easy to move around.
Wow. Okay, I love that.
To the expert, that entire complex expression takes up exactly one slot in their working memory. It might even take up 0 slots if it is completely automated.
That makes so much sense.
Right. True learning isn't about trying to increase your working memory capacity. Biologically, that's impossible. True learning is about moving knowledge from that fragile, tiny working memory, binding it into chunks, and storing it safely in the vast, stable architecture of your long-term memory.
But we can't just copy someone else's zipped folders into our own brain. If we want to build those chunks, we have to actively construct them ourselves, which means we have to step into the unknown, grapple with the logic, and inevitably we are going to make mistakes.
And this is where neuroscience completely dismantles the quote-unquote math person myth.
Here's where it gets really interesting.
Oh, it's the best part. For decades, students have internalized the belief that making a mistake on a math worksheet is evidence of a lack of intelligence. But when neuroscientists place students in fMRI machines and observe their brain activity during problem solving, the data shows the exact opposite.
The scans actually show what happens the exact moment a student writes down the wrong answer.
Yes. The instant an error occurs, the brain exhibits a massive, rapid increase in electrical activity. It produces a synaptic spark known as error-related negativity, or ERN.
Error-related negativity.
Right. This spark happens rapidly, typically within 50 to 100 milliseconds of the error. The brain is firing on all cylinders, trying to quickly resolve the conflict between what it expected to happen and what actually just occurred.
So a mistake isn't a sign of a broken brain. It is the literal physiological signature of a brain doing a high-intensity workout.
Exactly. Productive struggle, which is the act of grappling with a mathematical concept that is just slightly beyond your current level of mastery, is a biological necessity for learning.
It's required.
It is required. When you struggle, and specifically when you make and then correct an error, that intense electrical firing along the neural pathway signals specialized cells in your brain called glial cells.
Okay, I want to make sure we understand the mechanism here. The electrical spark from the mistake is essentially a flare going up, and these glial cells respond to it.
Exactly. The glial cells sense that high volume of electrical traffic, and in response, they begin to wrap a fatty substance called myelin around that specific neural axon.
Myelin, like insulation on a wire.
Spot on. Myelin acts as an electrical insulator. When a neural pathway is heavily myelinated, the electrical signals related to that math concept can travel significantly faster and with far greater efficiency.
So making a mistake, realizing it, and struggling through the correction essentially paves the roads inside our brain. We are upgrading our neural pathways from a bumpy, muddy dirt path to a high-speed multi-lane freeway.
That's exactly what's happening physically.
If you just look at a problem and get the answer right immediately without any mental effort, you aren't signaling those glial cells. You aren't laying down any new myelin. You're just driving on a freeway you already built yesterday. The struggle itself is the construction process.
And there is a really vivid classroom activity mentioned in the instructional design sources that brings this abstract biology into the physical world. It's called the crumpled paper task.
Well, this sounds interesting.
It's great. A teacher hands a student a crisp, perfectly clean piece of paper and instructs them to physically crumple it up into a tight ball.
Which probably feels so wrong to a student.
Right. That aggressive act of crumpling represents making a mathematical mistake. For a student, it feels messy. It feels like they just ruined a perfect piece of paper.
But then, the teacher has the student uncrumple the paper and smooth it out flat on their desk. And the paper is now covered in deep creases and structural lines that were not there a minute ago.
And then they take a marker and physically trace over those new crease lines.
Yow.
Yeah. Those marked lines represent the new neural pathways. They represent the fresh myelin that literally just formed in their brain specifically because they made a mistake, grappled with it, and altered their approach.
It provides a tactile, undeniable reminder that the messiness is the learning. A perfectly flat, uncrumpled piece of paper hasn't learned a single thing. It hasn't changed its structure. It hasn't adapted at all.
Exactly. In educational psychology, the environment where that crumpling happens is called the zone of proximal discomfort.
The zone of proximal discomfort.
Yes, it is the precise cognitive sweet spot located right between total boredom and overwhelming frustration. If a math problem is too easy, the student is bored, and zero myelin is produced.
And if a problem is wildly beyond their current capability,
Then they enter cognitive overload, their working memory crashes, and learning shuts down entirely. But right in the middle, where the problem is challenging enough that they have to test different methods where they get stuck and have to actively think their way out, that is the zone of proximal discomfort.
So what does this all mean? When you are sitting at that desk and you feel that wave of frustration hit you and your pencil is hovering over the paper, that feeling of frustration does not mean you are failing the assignment.
No, not at all.
It physically, biologically means you are currently learning. The discomfort you feel is the conscious sensation of your brain rewiring its own circuitry.
And understanding that biological reality requires a massive paradigm shift in how we relate to mathematics. Math isn't about being a human calculator who produces flawless algorithms on the first try.
Right.
It is about being an explorer willing to get completely lost in the woods, trusting that the act of finding your way out is exactly what builds your internal map.
I love that. But we really have to connect this cognitive science back to the very real, very physical reactions people have to numbers. Because, understanding the mechanics of myelin and working memory is intellectually fascinating, but applying it to a lifetime of math avoidance is where this research becomes genuinely transformative.
I completely agree. Anyone who has ever experienced math anxiety, that sudden tightness in the chest, the complete blankness in the mind, they need to understand that their experience is entirely valid.
It's not just in their head.
Well, it is, but you know what I mean.
It's a documented physiological event. When your cognitive load becomes too heavy and you become overwhelmed, the fear center of your brain, the amygdala, literally overrides your prefrontal cortex.
Oh, wow.
It hijacks the logic and reasoning center of your brain, making mathematical processing physically impossible in that exact moment.
And I'm going to repeat that because it dismantles so much shame. When you are in a state of math anxiety, reasoning is physiologically impossible. Your brain has pulled the fire alarm.
Exactly, it's a fire alarm. It is a biological threat response to cognitive overload. It is not because you are lazy. It is not because you are unintelligent. Your mental RAM simply crashed because there were too many tabs open and the system needed to reboot.
And that's why the instructional design frameworks we reviewed are demanding a fundamental change in our educational metrics. We have to completely remove the demand for speed.
Yes.
True mathematical proficiency, the kind of deep understanding that leads to actual innovation, has absolutely nothing to do with how fast a student can calculate a multiplication table.
And that is the core, validating message we really need to deliver to anyone who has ever cried over a math textbook or felt a wave of panic when asked to calculate a tip at a restaurant. Your job isn't to be fast. It's to think.
It's to think.
Math is about reasoning. It is about exploring complex patterns. It's about deliberately building those mental freeways over time. It's absolutely not about speed-writing algorithms you don't even understand just to be the first one to finish a worksheet.
Decoupling math from the pressure of speed changes everything. When we reframe mistakes from being evidence of stupidity to being the physical catalyst for brain growth, we unlock incredible human potential. We allow the working memory to finally relax, the anxiety tabs to close, and the actual beautiful logic of mathematics to be processed, understood, and chumped into lasting mastery.
We have covered a massive amount of ground in this deep dive. We've explored the surprisingly tiny limits of our mental scratchpad. We've looked at the dangers of the algorithm trap and how extraneous load forces us into mindless mimicking. And we've mapped out the messy, brilliant biology of how making mistakes triggers glial cells to insulate our neural pathways for high-speed thought.
The collective research definitively proves that when you struggle with math, the fault does not lie with you. You are experiencing a systemic clash between your brilliant, evolving biological architecture and instructional methods that simply were not designed for how the human brain actually processes complex information.
I want to leave you with a final thought to mull over. Something that takes these neurobiological principles out of the classroom and into the rest of your life.
Oh, I like where this is going.
We've established that the human brain physically requires the messiness of trial, error, and struggle to build lasting mastery. The perfectly flat, uncrumpled paper learns absolutely nothing. So if our brains are biologically hardwired to grow strongest, specifically through our mistakes, what other challenges in your life are you currently avoiding simply because you've mistaken a productive struggle for a personal failure?
That is a powerful question.
Right. The next time you find yourself sitting at a desk, staring at a complex problem, whether it's a multi-step algebra equation, a daunting career pivot, or a massive creative project, and your pencil is hovering, don't freeze. Let the paper get a little crumpled. Your brain is just getting ready to build a new freeway.